Actually, I'm going to present some preliminary work on the project, on the European project called Made3D, dealing with multi-material additive manufacturing. This is a collaborative work with Fraunhofer, University of Augsburg, CSEM, and of course, University of the Aegean. So you all know, I don't want to spend a lot of time on laser powder bed fusion. It's an additive manufacturing, extremely popular the last years. Actually, it enables to fabricate parts with reduced lead time. The challenge of the project is to print multi-materials. In several engineering applications, you need to bond two different materials, for example, aluminum with magnesium or aluminum with copper. And this is one challenge on this project. Currently, we would like to print aluminum on copper. The challenges are there. The first challenge, of course, is the interface, but we're not dealing with this part since it will be dealt in the last year. But and the first problem is the cross-contamination. Usually, the cross-contamination, there is some powder left on the gates, and actually this influences the quality of the printed part. So this of course has several degradation, and in this regard we tried to make some simulation of the different cross-contamination level. The part is this one. Okay, this is from AVL Electronics. It's also a project partner in the project, and this printing is for high power electronics is aluminum, and in this regard, we have to print some copper parts. So the strategy that we actually went through is. First of all, is a mixing of the powders with specific ratios. I will come with the next slide. The 3D printed with an SLM solutions machine at Fraunhofer, and of course there is the evaluation with XRD, SEM, and tensile testing. So the printing strategy was twofold. The first one is the different level of cross-contamination without non-contamination, 0.5 contamination of copper to aluminum, 3% copper to aluminum, and 5% copper to aluminum, plus, and another variable was also the build job. This is upright, 45 degrees, and horizontal. So when you try to see macroscopically how the powder gets mixed, so then you can visually check without any contamination, 0.5, 3%, and 5%. It's difficult, of course, to quantify them, but we have already done it at the lab. And taking some samples at from the SEM, showing that, for example, this is the powder higher magnification of aluminum. Okay, this is of copper. In case that we have 0.5 contamination of aluminum, then you can see 1 or 2 aluminum powders into the samples, then it's much more evident. With higher contamination, you can see the powder of aluminum has higher dimensions than the diameter of of the copper powder. And of course, at higher contamination, for example, 5%, then you have something like interconnection between the aluminum particles. So now here we have two different cases. The contamination of copper to aluminum. For example, here you can see that for the 0.5 copper contamination, you have the peaks showing aluminum and copper, and the contamination of aluminum to copper, we found some similar results with different peaks. As I told you, still it's a preliminary work. Unfortunately, we didn't finish the contamination or the tensile test of the contamination of aluminum to copper. That's why I'm going to present you only the contamination of copper to aluminum. And here you can see the tensile test results regarding the different build jobs with different also copper contaminations. As you can see, all contamination increase the yield stress. And this is typical because, of course, you have copper addition in aluminum, and there is a possibility to form some intermetallics. That's why you have an increase in yield stress, and of course, the same applies to ultimate tensile strength. Regarding ultimate tensile strength, here you can see that in general, all contaminations for the low contaminations, you have a decrease in ultimate tensile strength, but with the higher contamination, of course, you can have something like ultimate tensile strength is reaching the nominal values without any type of contamination. Of course, this is something like due to, of course, to the intermetallics and of the copper addition. The most interesting results come from ductility, tensile elongation at fracture, showing that all contaminations have a poor effect on tensile ductility. And this is something that we expected, since the contamination actually acts more or less as stress raisers. And this decreases the tensile ductility. Of course, you have some variances with the printed, with the horizontal print job or with inclined 45 degrees. Actually, you have a decrease for the red symbols. You have a almost linear decrease, except of the low contamination level. Of course, we possibly have to repeat some tensile tests. Now that I show you all the tensile test results regarding the yield stress and the tensile ductility, what is missing, or it's extremely sexy for the cast materials, we also have some quality indices just to denote the overall tensile performance. For example, in the 80s, there was a guy called Druzy from France, denoting this kind of quality index, denoting that Q is the quality in terms of mechanical performance, RM is the ultimate tensile strength and elongation at fracture, and this is a coefficient come from expertise. So, but right now, up till then, there was some other over the next decades, another quality index came to the that merges yield strength and strain energy density. Strain energy density is actually, as you can see, it's the integral below the tensile strength curve, and comprises better with the energy, with the strain energy density. It's called strain energy density, or with the energy needed for the material to break. So, and according to the theory of C, it is the strain energy density somewhat proportional to the fracture toughness of the square of the fracture toughness of the material. So in this regard, we have used this kind of quality index to interpret all the tensile mechanical performance of the printed job. And as you can see, these are the results of the quality index. I will step one by one, showing that this is a diagram of yield stress over strain energy density. And of course, these dotted lines are the ISO quality curves. As you can see, starting from the 90 degrees, this is the without any contamination, and with increasing contamination, you see that the quality slightly decreases. For the vertical material, this is the one that is on the blue lines. Here you also can see that with the increasing contamination, you have a significant decrease in the quality of the material, and then there is a recovery at the higher contamination, of course, due to the excess copper. What is challenging and needs to figure this out is the 45 degrees that seems to be less immune to the cross-contamination. For no contamination, this is the only exception, the low contamination, then you have a drop in the quality. But for higher contamination, that you see that there is a steady quality of the material. So, in this regard, we found some very nice results that might be helpful for the design engineer to check, or if he is not sure about the cross-contamination, then he could easily decide on which printing solution or printing build job he can facilitate, he can take. So the conclusions, the preliminary conclusions of this study is that our main goal was to assess the effect of different contamination. In this regard, we have made different levels of cross-contamination and different build jobs, and the quality levels are, the quality maps are here to help for the design engineer to help for the decision of the build job. Well, I would like to thank the Made 3D project for at least it's the first year of starting this project, for realizing this research. Thank you very much.